after this, we move on with what is called Monte Carlo's method. So Monte Carlo's, can you hear?
Yo creo que te está un poquito más fuerte. O así. Está prendido. Sí, sí, sí. Perdón.
Right? Okay. So Monte Carlo's method were born in the 1940s, and the name comes from the Monte Carlo place in the nice coast of the Mediterranean Sea. And the name comes because one of the father of the Monte Carlo's method, Lams, remember that his uncle would borrow money from the family because he had to go to Monte Carlo. Now, you can imagine what's going on, and that's where the name came from. Also, while he was playing solitaire, the card game, was trying to calculate the likelihood of winning based on the initial layout of the cards. And he tried to do combinatorial calculations, just to solve it for first principle there. And he decided that was not going to get him anywhere, and so he decided to go for the practical approach of actually trying out many different layouts and seeing how many times he was successful at the game. And so he realized that for this you need a computer. And they ended up, Samulan and John Neumann, developing algorithms including rejection sampling, which the one you have seen first hand right now, and then something called important sampling that we will learn about later. So when we talk about Monte Carlo methods, there are two broad things that go under the header of Monte Carlo methods. One is Monte Carlo error estimation, and the other is Monte Carlo Markov chains. So let's start with the first one and go back to parameter estimation and confidence region. And let's think about the conceptual interpretation in cosmology. You have a set of parameters, alpha 2, which is only known to Mother Nature. And then this is statistically realized in some set of parameter alpha. You should imagine that this is a vector with all your parameter omega matter, omega lambda, equation of state of dark energy, etc., etc. That are the one of the observable universe. And then you make a measurement where you see whatever you see on your measurement with its errors and all its limitations, and you get some data which are measured. And now you do some analysis and you get some alpha or 7 or 7. So you, the experimenter, can only see this alpha here. But what you really wanted to know was this one. And of course, this is not a unique realization of this one. First, because the observable universe is one possible realization of this one. And second, because if you went to repeat the experiments, maybe the errors will be different. And so we get to know this, and we would like to know this, or at least we want that the error bar around this quantity includes the true value. So remember, when I say the name of the game is not how small your error bars are, but how they get transferred. So the name of the game really is, it doesn't matter how small is the error bar around this quantity. I mean, can go from 1 infinity to infinity. What you want is that this is within the error bar. Otherwise, we're talking nonsense. Okay, so that's what you want. And of course, your approach could be, well, there could be infinitely many realizations, hypothetical data set. So you only get to have no D0, but you could get D1, D2, D3, blah, blah, blah. Each one with specific parameter, alpha 1, alpha 2, alpha 3. So what you would expect if you your experiment is not biased is that the average of all this alpha will end up being the true one, which is what you want to know, in the limit where you have infinity of these. Now, if I knew the distribution of the shift alpha I minus alpha true, that's all I need. Right? Because then if I know the distribution, I measure alpha I know this distribution, so I know how to put an error bar so that this alpha true is inside the error bar. Fantastic. However, you don't know that. So the trick is to say, oh, well, maybe the parameter alpha that I end up observing are not too far away from the true one. And so, what you can do, you can try to simulate the distribution of the alpha I minus alpha observed. And so, then you say, aha, but then maybe this distribution is not too far away from this distribution, and so I can just live with this distribution, and that's all I need. If you're willing to buy this, then we complain, right? Because you can make many synthetic realization of universes where alpha naught, which is the one you end up observing, is the true. And you can mimic the entire observational process in all these mock universes, estimate the best fit parameter from each, and then map the distribution of the alpha synthetic minus alpha observed. Now you have this, and then if you are willing to accept that this is this, that's all you need. Or a good approximation of this one, that's all you need. So it's extremely important too. So for those of you who happen to work on the BOSS Baryonic Acoustic Oscillation project, or those that have read those papers, you would see that over and over and over again, they refer to the MOCs. So take any of those papers and check how much the analysis relies on the MOCs. When they rely on the MOCs, what they are doing is exactly this. They go one step beyond that and they say, well, I don't even simulate this. I simulate this minus a fiducial one. So even before I do the experiment, I say the universe is not too far away from vanilla lambda CDM. So you don't need alpha observed. You can start doing the MOCs before you even get the data. If you are willing to say that this distribution, where this alpha naught is the alpha fiducial, it's a good representation, it's a good approximation of this. Is there some problem between this, do you think? Could there be a problem? Yes. So these are, so you generate many MOCs, many synthetic realization, and you analyze those like you would analyze the data, and then each time you get some problems. So somebody else had the time up, and now I lost the hand. Oh, so the question got answered. So if you really want to be the advocate of the devil, you can say, what if alpha true has got nothing to do with alpha fiducial? That's fine. So you have to assume that. If that doesn't hold, then all bets are off. If the universe is not a lambda CDM and it's something completely different, all bets are off. However, whatever the universe is, it's likely not to be too far away from a lambda CDM because lambda CDM works so well. And so that's what gives us hope that this procedure works. Okay. So after that, we move on to other things that goes on the Monte Carlo method, which is what you are eagerly waiting for. It's Markov chain, Monte Carlo Markov chains. So Alan already went through this exercise. If you have to explore a likely surface, you can try to do a grid-based approach. So if you have the parameters, say omega matter and sigma 8, you can grid it up, and then you can go and do your analysis for. So if you have the parameter, and say you put 10 sample in each of the parameter, then you have 10 by 10, maybe you can do it. Now let's just take the vanilla lambda CDM model. If you don't want to explore anything fancy like a good ordered energy, you have, say, 6 parameters, you take 6 parameters, let's put 20 pixels per dimension. This gives you almost 10 to the 8 evaluation. At below 2 seconds per evaluation, you need too many days. Then you can play a little bit with that if you want, but imagine you want to, do the analysis more than once. Imagine you want to do your analysis not just on the data but also on your logs, then this is obviously not viable. So you have a problem. But let me ask you one thing. Let's learn from nature. Spot the differences between the picture on the left and the picture on the right.
The clock.
The clock.
Okay, what is your eye doing while you're trying to spot the differences? Your eye is constantly jumping around the picture, right? Your eye is not making a grid on the picture and going grid point by grid point, seeing what's going on. That's why your eye is so efficient or inefficient, depending on how you set up this problem to pick up the differences. And the other things that really surprised me when I saw it was this. So this is a picture. Can't see too well, but this is a person that you see from the back, and this is person that you see from the front. And these are people have tracked how the gaze explores this picture from different people. So basically they were asked to look at the picture for 3 minutes. And they were checking where the eye was focusing. So as you know, when you see, you don't see the entire picture, even though you think you are seeing the entire picture. What you really see, you are focusing on a very small part of the picture, but your eye moves constantly. And so your brain reconstructed the entire picture. And so you see, you're not exploring it like a grid. You're not even exploring it uniformly. Your eye is exploring it by spending a lot of time around faces. So we are trained to spend a lot of time looking at the eyes and expression of people. Because there's a lot of information for us enclosed there, so we spend more time there. And then we spend time around lines or salient patterns. Okay, so our eyes somehow do something like that. So let's try to put it a little bit more mathematically. Let's give us a simple problem. What is the mean of a large number of objects? So what's the mean height of people in some place? So you can say this is the sum of the height over n. If n is very large, this becomes untractable. So you can say, let me take a fair sample of this population and just do this. Exit codes, and things like that. So in probability, you just say, I want to approximate f of x times the probability distribution of x as that. Any Bayesian inference So you can show, and this was somewhat included in this exercise of Alan, that this estimator is unbiased and you can quantify the variance of the estimator and it shrinks like the size of the computation by 1/2. So that's why Alan said, I give you the 10,000 points because then I know what kind of error you have on time. So let's motivate this a little bit more by introducing an historical method. So this is Enrico Fermi, and so really the beginning of Monte Carlo's method, although they were not called Monte Carlo's method and people didn't even know what that exactly was with Enrico Fermi, who liked to surprise his colleague by making very accurate prediction of experimental results, and people didn't know how he did it. And he revealed that his guesses were derived by statistical sampling techniques, which is similar to the one we are discussing here, that he used to calculate when he was having some. These are Stan Ulam, which is the one of his uncle, the one of Monte Carlo, and the one of the solitaire, and this is the one on. So Ulam and Van Neumann suggested that these techniques that he started developing at Marine could be used to help researching nuclear fission at Los Alamos, and could be aided by computers and based on computing chances. So since the program was top secret, they couldn't say what it really was. So that's why they call it Monte Carlo. So people didn't know what they were talking about, but of course they were talking about doing nuclear explosion. They needed computers to do that, and that was the time transitioning between when the computers were women. Array of women when we gave them the calculation to do and then put the result together, and real computer will start being. Another thing that that I find very interesting, although I don't know how it actually works, is the Fermi. This is Fermi analog of a Monte Carlo simulator to study the diffusion of neutrons. When you do nuclear explosion, that's the hard thing to solve. And so he ended up writing an actual machine where you have to put in by hand something that was the diffusion length, and then you could actually do some Monte Carlo, but analog. Don't ask me how it works exactly, because I couldn't figure it out. So the first major Markov Monte Carlo paper was published by Metropolis in 1953, but he had to wait until 1970 to get a generalization of his algorithm to the Metropolis-Hastings algorithm, which led to the explosion of the Markov Monte Carlo. And later on, I wanted to actually go through that algorithm that is at the base of all the Monte Carlos. So, what are Monte Carlo functions? You have a higher dimensional probability distribution, and you want to sample it in a way so that what you sample ends up being proportional to probability distribution. And you decide to sample to the random walk, similar to what your eye does when exploring a condition. So you start at arbitrary points, take Markov step, and then you decide how to do that. And your goal is to get the density of points. Imagine that you have a two-dimensional problem, proportional to the probability you want to explore. So, as you have seen with presentation, well, you've seen this actually animated on the first day. You start walking, and then you stay there, and eventually you get this like cloud of points. So what this does, it gives you an approximated correlated sample from your target distribution. Now we're going to see in a minute how you're going to do that and what is the problem that you have to solve to do that. But this seems reasonable, right? You want the density of point proportional to the probability, and then you just work with the density of point. So this is standard in CMB analysis. CosmoMC does that, Monte Carlo does that, MC does that. There is things in Cosmosis to do that. And I'm sure some of you that go through the exercise will have seen this or will see this. So you want to simulate the posterior distribution, and you use Bayes as usual. This is the measures here. This is, for example, the measure power spectrum and the measure VAO shift. This is the set of cosmological parameters. This is your prior, and you want to sample from this. You want to generate random draws from the posterior that are a fair sample of where things are non-zero in this multidimensional parameter space. So I want to put this in to remind us that we have to deal with likelihood and we have to deal with prior. And imagine that this is your likelihood, and imagine you want to discuss the sheet class. So that's the real sheet, and then as you move away, you end up with something that looks like a sheet, but it's technically not a sheet. And so if this is your prior sheet class, what you will end up sampling for is the posterior, which if the likelihood is big enough, it's going to be close to the sheet, but maybe not exactly considered to the peak of the likelihood. Now, since using software as a black box is always a bad idea, let's just walk through it. So you want to do parameter walking parameter space at each step, sample one point in parameter space, and at the end of the day, you want that the density of sample point is proportional to the posterior distribution. That's what you want. Now, why you want this? Because it's fast. Because before you had them to the 7 likelihood evaluation in the example that I gave you, while now you can live with much less than 10 to the 5. And we have seen why in this example. And in this example as well. That was a rejection sampling, but the problem is obvious. As you go to higher dimension, and you have some localized blob in this higher dimensional space, and you're interested in that localized blob, most of the space is actually uninteresting. So that's why the grid is so inefficient. Also, remember that what we want in cosmology is many times to plot marginalized constraints. Remember, I don't know if you actually went to the Planck document that they told you go and check how many nuisance parameters they have. Do you remember the answer? How many nuisance parameters they have for the foregrounds? So it depends whether you are looking at the temperature only or the temperature and polarization, but it's more than 90. So at the end of the day, what you want the result marginalized over at least the nuisance parameter, if not all minus 1 or 2 of the cosmological parameters as well. So imagine having to do an integral in that many dimensions. Even summing over grid, that's unmanageable. But now, if you've done something like that, you've done something like a Monte Carlo integration. And Monte Carlo integration is very easy because what you simply do, you just project and sum the points. So now it doesn't matter in how many dimensions you have sampled. You just read up all the points, forgetting about what label that point had in the coordinate you're not interested in. So that makes it really, really easy. And also the next thing is that adding external data set is often very easy. You can do it in a dumb way, which is wrong. You can do it in the right way, which is not dumb and it's right, and we're gonna go through this as well. So let me show you how to do it operationally. And now I'm gonna jump around so you really remember this, even though it's not written there. So the recipe goes as follows. Start at a random location in parameter space. So let's say that the parameter space is two-dimensional, just to simplify things, and let's say that is, the floor. Let's say that you have, the floor is not flat, right? So at each point in the floor, you have your posterior, which get a different value, and also compute, at each point you compute the likelihood, then you evaluate it. And then there will be some point where the likelihood is maximum, and some point where the likelihood is basically zero. So what I would do, I would take a random step in parameter space. So since the parameter space is two-dimensional and this is this floor, I'll just take a random step off. So now I'm at this, and I compute the new parameter and the new likelihood. Now, if the new likelihood is better than the old one, so if in this direction I'm going towards the maximum likelihood, or at least I'm going up here, I accept and save the step. So I write this set of parameters and its value of the likelihood in a file, and I accept it. Sorry.
What do you mean with better?
Sorry?
What do you mean with better likelihood?
So you would have a routine that you reads the data, reads the model corresponding to those parameters, right? Has a covariance matrix, has an expression for the likelihood, and just spits out a number. That's the value of the likelihood at each point. Then you take another point, they call the routine again, you get another value of the likelihood. Is this second likelihood better, that is, the number is larger, or is worse, it's smaller than the previous one? So if likelihood at the new point is greater or equal than the old one, until here, I accept the step, write it down, now new becomes old, and I start again. However, if I'm moving in the wrong direction, let's say I go here, take the new parameter, new likelihood, old parameter, old likelihood, compare the two, and the new one is worse than the old one. If you just wanted to find the maximum, you just throw it away. But here the game is not to find the maximum, it's to find the maximum and have a good estimate of the error bar, so a good sample of the distribution. So at this point, you throw a random number uniform between 0 and 1, and then you decide, depending on what the number comes out, if this x is greater than this ratio, do not take the step. Save the old one. If it's the other way around, then accept it. Go back. So that's why this was being called the walker by some of the presentation. Because you imagine this being repeated, you see, yes, no, yes, no. Eventually, right, with a random walk, you will end up having explored properly the parameter space, but having explored the parameter space in a smart way, where you spend most of the time where it matters, and you spend very little time where it doesn't matter. So now, this is all clear? Okay. However, you still need a bit of information. If I now tell you, do that, you need a piece of information, a crucial piece of information. What do you think that is? So imagine, the data you have then, the likelihood, somebody gave it to you, the model is come. What piece of information do you need? Take a random step. So I told you take a random step. What is take a random step? Well, I could have taken a big step, a small step. I could decide to step in one direction or in the other direction. what is that? So the probability distribution on how you take that step is called proposal distribution, which you should not change once the chain has started.
It's probably not another question, but what will happen if you are like, in an area where the likelihood is good, and around it there's bad likelihood, or it's not? I don't know, like outside if there's a better likelihood. Yeah.
Right. So that's exactly the nightmare for anybody that wants to run MCMC. Right? So there are ways around that, but you are never 100% protected by a case like that. So we are very lucky that whenever you do application with the cosmological background, the likely surface is extremely well behaved. And since you almost always end up using that together with other data set, and by that point, having multiple peak or having a local maximum which is not a global maximum, that probability is very low. It's still be there. I mean, many people may have an idea about it, especially when you try to do this for math regression estimations. I mean, the problem is there. There are ways around it. You're never 100% protected. Yeah. Okay, so the proposal distribution you should not change once the chain has started. Because otherwise, what you end up with is not a Monte Carlo number of chains. What you end up with is not something in which the density of point is proportional to your posterior. You will end up with something. It may be that you will have to recycle that something in some way, but it's not what you want to do. So the proposal distribution or step size for friend, it is crucial to the MCMC efficiency. Now there's a theorem that says that even with the dumbest possible step, if you have available the age of the universe, you will eventually get there. But the problem here is not to eventually get there, to get there in a finite amount of time with a minimum amount of evaluation so we can get results. So the key is to get this proposal distribution. So step too small will lead you to what is technically called mixing, and steps too big will give you to what is called the poor acceptance rate. So let me give you an example before I show you some plot. So imagine that the likelihood is distributed as this cable here. There is a cable here, so this two-dimensional surface is not completely flat, there's a little bump in there, and that's where momentum is pure. But imagine that my step size is this. That's obviously too big. It's very unlikely for me to hit that. And the moment I actually hit it, it's very, very likely for me to step out from it and it's gone. Or never step out of it unless for random draw, you remember, then you end up stepping away from it and then you will never get there. So, too big step give you a poor acceptance rate. And you want to fair sample of the likely surface. So here are some examples of output from a worker from an MCMC. Here is the step number, and here is some renormalized value of the line, or it could be the value of a parameter. The plot will be very, very similar. So, imagine your step is too small, and this is the value of the parameter, you see. This is a very poor exploration. Imagine that the step is far too big. It's also accept very, very little points. Because look, it stops here, never takes a step, it stops there until it takes a step, and then it stays there for a very long time, and then it takes another step. Obviously, it's going to take forever to explore the full parameter space because the worker is not moving. while this is the right thing. That's the kind of thing you want to see when you have the right proposal distribution. So in this case, you can imagine having something like this, right? That if your step is this one, it's, you know, maybe right in this direction, but obviously too small in this direction. These kind of problems where maybe your likelihood has got this shape and your step has got this shape are obviously going to lead you to stay thinking forever to explore. So let me visualize in a different way. So this is your target distribution. This is a bit of a nasty example, which goes back to your question, because the target distribution has got two things. And this is a too small step size. You never get to see the other one, you just find one of the two, because the step size is not big enough that once you fall into one of these holes or peak, you never get to see one. If your step size is too big, you will see the other one, so this is your target, this is what you see. But it's very, very badly sampled. While if you get it right, the MCMC approximation of the target distribution is actually not too bad. Of course, that's for a fixed number of likelihood evaluation. Of course, if the number of likelihood evaluation goes to infinity, eventually you will get it, but you don't want to get that. And the other thing, so for statistician, this is transition operators, so obviously you transition from one position to the other. The other thing is that in principle you want to satisfy what is called the tail balance. The tail balance means that I'm equally likely with my step, including the likelihood to go from here to there, and it is to go from there to here. Now, next to the boundary, this is not the case, right? Because if I have a sharp boundary somewhere, given by some prior, or because you just told you to only explore up to here, then of course if I one viable part of the boundary, I won't accept a step that is outside the boundary, and so this is obviously not reversible. So I wonder if we should take a break now or finish. Yes, let's do that. The other thing you want to be aware of is that the MCMC needs to have forgotten about the initial starting location and as well explore the parameter space, then you're ready to do a parameter distribution. This is a zoom in. You see there are a few steps of an actual MCMC. This is the log likelihood. This is what is called the burn-in. Remember, you start at a random point in parameter space. The random point may have nothing to do with the maximum of the likelihood. So you take the walker sometimes to walk around until it gets the interesting part, so that bit needs to be removed. And this is another example of two walkers. So one walker started from there, the other walker started from there, and they go. And this is the distribution of the sample point in two parameters. This happens to be the power spectrum block, and this is the amplitude of the power spectrum, also all the data. And so if you had only the red walker, you would say, fine. The mean value somewhere there. If you had only the green walker, you say, fine, the mean value somewhere there. Neither of them is correct, because neither of them have well explored, sufficiently explored parameters. So neither of these two chains is what is called in technical world converged. So you need to use a mixing and convergent criterion that will tell you when you are done. So I want to give you an exercise now, and we're going to see how much time we're going to take, which is the following. And then I'm going to tell you what is the mixing criterion, etc. I want you to get some data and explore the parameter space with an MCMC, with the Metropolis Hastings algorithm, describe by jumping around here. We can be more adventurous and try to parameterize Hubble as a function of redshift and S-splines in beings. You can change the equation of state parameter, but the simplest one you want to do, you might just use lambda CDM and just explore that. Now, if it's just a lambda CDM, it will be a little bit dumb because it's few parameters, and for few parameters you are more efficient using a grid than using an MCMC. But a good exercise to write your own MCMC engine and see at work and do all these plots of step size versus likelihood, step size versus parameter, and see how the worker explore the parameter space. So I leave you here the equations. That's the equation of the Hubble as a function of redshift for various parameters. And you can get some Hubble as a function of redshift data from there. Or there is a little directory in the exercise file directory, which is also called H of Z. Data, in there you have the data, the error bars, they tell you you should use a Gaussian likelihood for the data uncorrelated, at least at this level of the approximation. So, since this exercise may actually take a little bit of time, you have to use the random generator, you have to think about what you are doing. I know that one of the group that is doing project actually is doing that.
Yes, Juan Carlos Hidalgo is the leader. I don't know if he's...
Well, who is in that group? We don't need necessarily the leader. We need people that have seen this before.
The people that is in Juan Carlos projects can stand up, please.
Everybody else is still running MCMC?
The people that is in Juan Carlos team can stand up, please.
So, your team, did you end up actually writing the little MCMC engine already? Or you're doing that today? Because I thought that they could help everybody else to try to do that. Tomorrow they can.
I thought we were...
Why don't we just give, so we're going to take a break now because it's enough time, and then we're going to see how that goes, and then if...
There's a couple of them.
Okay, because the idea was that they may help also with the other ones, because maybe if you just start from scratch, then it will take much longer, but if somebody knows already, can help the other groups. Okay?